We are hosting here a webinar on mitigation banking. We call it Mitigation Banking 101. My name is Beth Euler, and I'm the Pennsylvania Director for the Center for Watershed Protection. And I'm here with Allison Gibson. Many of you probably already know her at Lancaster Clean Water Partners. She asked us to kind of co-host and assemble this webinar. It will be recorded, as you saw as you logged on to the Zoom. So we'll make that recording available after this this presentation is complete, and you'll be able to refer to it in the future. Just to go over a brief agenda, I'm going to turn it over to Allison here in a couple of seconds to kind of give a little bit of the background for the reason behind getting everyone together here today. I'll provide a background and some speaker introductions, and then we'll have presentations by Dave Gorman at Pennsylvania DEP and Ward Oberholzer at Land Studies / Century Engineering, and then we'll have some time for Q&A hopefully at the end. So Allison?
Sure, thanks, Beth. We really appreciate your help and leadership here with setting this up. So I'm just taking everybody back a few months. The Buffer Action Team gathers about every quarter, and it's a group of experts in Lancaster County that talk about what are the biggest opportunities and how are we going to meet these big goals, and what are some of the needs that we have in order to do that. And one of the things that we realized that our partner organizations needed and we're asking for was a little bit more of the background about what mitigation banking is. Some people were experiencing that with phone calls from landowners that they've been working with. Some people had heard about it through a funding program. Some people have maybe been working with contractors who are also doing pieces of that. So we needed to get everybody on the same page. What are the basics of this? So that's why you see the title of today is Mitigation Banking 101. Just what are we talking about here? What is this tool? Because in Lancaster County, we have these big goals for nitrogen, phosphorus, and sediment reductions. There are so many different best management practices that can help get us there. And mitigation banking and a whole watershed approach, the way that they interact together is pretty unique. And so that's why we just need to understand what it is and how is it working? How is it a tool in the toolbox to help us achieve those goals? I think a lot of us are really curious about some of the science, some of the calculations, some of the interaction with different partner organizations that play different roles in that process. So today we're intending to get everybody on that same page, understanding a little bit more about how this tool can help us achieve those goals. We're not going to have all the answers by the end of 60 to 90 minutes today, but just wanted to provide this opportunity to hear from some experts who have been doing this, who know some of the background about where this came from and how it is set up, so that then we can keep asking questions and we can get to a better understanding from all those different best management practices. How do they best fit in to this watershed approach, to Lancaster County's countywide action plan? That's a whole list of practices, but understanding how each of them best fits in is one of our goals today. So our Buffer Action Team, a shout out to you for really prompting this and getting us started on the pathway to learn more and to understand how we can work with lots of different partners across the county to help us achieve those goals. So Beth, thank you to you and our speakers today for helping us do that with today's opportunity. I know there will be more in the future, and this is just one of those starting points. So huge thank you to you.
And thank you, Allison. I wanted to just say a little bit about Center for Watershed Protection, because a lot of people in this room is very familiar and knows Allison and Lancaster Clean Water Partners very well. You may say, who is Center for Watershed Protection? We're a national nonprofit that was founded in 1992. We have a mission to advance clean water resources. We're a technical organization. We have about 22 staff members, and about a third of our staff are professional engineers. We're based in Fulton, Maryland, and do a lot of work in the Chesapeake Bay. I joined the center at the end of 2022 as the Pennsylvania director, as I mentioned earlier. I've got about 20 years of experience in the water resources field, focusing on stormwater and wetland and stream science and regulations. And I went to Shippensburg University, but I grew up and still live just over the border in Western Chester County. So I'm familiar with the area and share many of the same experiences as some of our conservation partners in the room today. Just a little bit of housekeeping, standard stuff. If you guys haven't already done so, if you wouldn't mind just entering your name and affiliation, you don't have to put something like you learned today in there, just your name and affiliation in the chat box so that we have a record of who actually did join us today. And then as the presentations are going on, just feel free to pop questions in. We'll try to hold them to the end unless there's anything really urgent. I'll be monitoring the chat, and you know, if there's something that we can address right away, we'll do that. But otherwise, we'll let the presenters go, and so that we can ensure we cover all the material for you today. And then, yeah, and in addition to questions and answers, if anybody just has anything they want to contribute to the discussion during the Q&A, you know, feel free to enter that into the chat as well. And Alison, I think, mentioned a lot of the background and the impetus behind this webinar today, and I think just to kind of expand upon that a little bit, we all understand the need for restoration in general in our communities. And just here in this picture, we see a stream bank that's severely eroded with my daughter when she was about 3 for scale, you know, causing all of the sediment, nutrient pollution, and stream impairments that we are trying to address. And of course, there are several drivers for undertaking these types of projects, stream floodplain or wetland restoration projects. And some are voluntary, you know, some are more grassroots to improve the quality of water in our communities and downstream. But however, a primary driver is regulatory. You know, whether we want to admit it or not, a lot of what we're trying to do is to achieve these objectives that have been placed, whether the TMDL objectives through the Watershed Implementation Plan, or meeting municipalities' NPDES MS4 permit pollutant reduction requirements, or finally mitigation banks to offset impacts to stream and wetlands through proposed land developments or roadway expansion projects, which are regulated through Chapter 105 of the Pennsylvania Code, and also Section 404 through the U.S. Army Corps. So you know, there are a lot of different factors going into some of these bigger projects that we see happening, and some of them are large-scale MS4 projects, possibly. Some of them are Chapter 105, and we'll get into that a little bit further. Terminology is important as we proceed through. We talked about this a little bit. This is kind of an ongoing conversation. Depending on the type of restoration you're talking about, stream bank stabilization is maybe not even a form of restoration as much as it is protecting infrastructure, you know, and armoring stream banks so that, you know, our roadways don't fall into the ground. You know, so stream bank stabilization isn't the same as floodplain restoration. So there's an importance in recognizing the difference in terminology as well as we proceed through the webinar today. And so our speakers will talk about the regulatory considerations and the design approach, what these types of projects look like, what sites they might be landing on to you know, suit a mitigation bank project. And finally, to introduce our speakers, we have Dave Gorman is a water program specialist at the Pennsylvania Department of Environmental Protection in the Division of Wetlands, Encroachments, and Training, Bureau of Waterways, Engineering, and Wetlands. He's responsible for providing permitting and technical expertise on a wide range of issues involving waterways, wetlands, and floodplains. His recent work is focused on aquatic ecosystem restoration, mitigation banking, and aquatic resource research and monitoring. Dave has worked in the division since 1993 and has a BS in degree in the biological sciences from Clarion University in Clarion, Pennsylvania. And I will go ahead and introduce Ward 2, but he will be following Dave's presentation. He's currently employed by Land Studies and Century Engineering, and is a professional engineer licensed in Pennsylvania and Maryland with over 30 years experience in stream stability and restoration. He's worked extensively in Maryland and Pennsylvania, completing designs and the implementation of stream and valley floodplain restoration projects, including watershed scale mitigation banks and those impacted by legacy sediments. These projects include waters with drainage areas over 30 square miles to smaller valleys with slopes greater than 20%. So we have two great experts that will be providing and sharing their information today, and hopefully answering some of the questions that Allison posed earlier that some of the conservation partners are curious about. So with that, I will ask Dave to share his screen and begin his presentation. Are you able to share your screen, Dave? I saw Dave on there somewhere.
Sorry, I'm still on mute.
That's okay.
Getting there, juggling all the different screens I have open.
Yeah, I totally understand that. I just want to make sure I have the right setting for you so that you can share your screen.
There it is. I lost the webinar window. Yeah, it's not showing a share button on.
Okay, let's see
Oh,
here.
no, there it goes.
You
Sorry.
got it? All
Yep.
right, great.
Screen 2, share.
Perfect.
All right. Did that come up?
Yep, it looks great.
All right, guess start off on slide 1.
All right, thanks, Dave.
Yep. So good morning, everyone. I originally approached this presentation from a different perspective, and then in talking to Beth, understand that the group is more interested in the under or inner workings or underpinnings of mitigation banking. So a lot of the slides, what you'll see is more restoration and technical aspects that we apply to these projects, but I'll try to do the narrative. I'll be deviating from what I had written to try to work in what your interest is and go forward from there. So I may hesitate or kind of look for words here and there while I try to figure out what to add to the slide to help integrate it into what banking is. As Beth said, I'm divisional wetlands encroachments and training. I think one of the important things, it's important to note that the process that we use for mitigation banking has been something that evolved out of EPA's 2000 publication of Principles of Wetland Restoration. And this has been applied to, especially in the legacy sediment world, and understanding how to restore those environments. As that process has evolved, we quickly, when mitigation banking came in around 2008, quickly had already been working on identifying ways to improve stream restoration, because the current approach to stream restoration at that time was woefully inadequate, to be kind. And you know, if we're asking permittees and others to pay millions of dollars in mitigation requirements, or requiring compensatory mitigation that adds up to millions, we wanted to make sure that the products that we were putting on the ground were meeting the intent of the rules, as well as effectively using people's money and time. And the current state of stream restoration in the mid 2000s was not at that point. So I had been already spending a couple years looking through a work that's been done around the country, and at the same time as the legacy sediment removal work was developing in science and underpinnings of that was developing, there's a lot of work going on in Western United States and Northwest US that dovetailed perfectly with that work, and the results were pretty astounding. And that was mainly geared towards restoration of salmonid habitat and undoing the degradation that occurred in the 1800s in the Northwest US. So So this whole process is iterative, and these are high level, principles that we operate under, and so we've learned a lot. There's still a lot to learn. There's still improvements to be made. I guess is one of the points to make. But I think we've come a long way in the last decade and a half compared to where we were, and unfortunately, not a lot of people have come along with us yet in this journey. Although we've been very successful in the mitigation banking industry because we've held this industry to this standard from day one. And I've had, many meetings with executives and being called in offices because of that approach, but it has been very successful. And just to kind of give you some idea, well, we've done over close to 60 miles of stream restoration now related to mitigation banking across all of Pennsylvania. So all aspects of the environment in PA, physiographic conditions, urban, semi-urban, and rural. But I think it's important for people to understand when we're talking about restoration, the Waterways Management Program, Wetlands Protection Program, we utilize the definition of regulated waters of the Commonwealth, which include floodplains. Those are regulated waters of the Commonwealth, or floodways, depending on who you are as an applicant. It changes which one we use. However, we use that, and it fits well with the science. So that both the science and underpinning and the regulatory program fit together very well in this respect. So when we talk about restoration, we're not just talking about the bed and banks of the stream or the ordinary high water mark if you're using federal lingo. We look at the whole valley, the whole floodplain and its valley. And so there is a difference when you do that. And Ward I know will cover some of this later, and I'll cover a little bit of it. But that is really one of the underpinnings of this is looking at the whole the resource as a whole and not partitioning it, and understanding it's the whole valley and floodplain valley and its history, not just what's going on today and what current conditions look like, understanding the alterations historically. And we'll talk a little bit about that. So banking, that's the way we approach when mitigation banker approaches us. This is the first lesson we have in Pennsylvania with a new banking company that comes in, is this is the way we do it. If you want to come in and do stream bank enhancement or stream channel enhancement, you're going to have a tough time as a mitigation banker in here, because you're not going to gain a lot of credit and it's going to be a difficult process. So a little bit of understanding of where DEP is in terms of this crediting, what ultimately boils down to a crediting process. DEP had proposed and finalized and implemented last March a function-based approach to aquatic resource crediting. This looks at the resource as a spatial unit, not a linear unit, similar to the way we define the science and an approach, asking questions and investigating conditions of the resource. So that was a major shift, and unfortunately, it drew the ire of a few constituents in the regulatory arena, and the then acting secretary in January rescinded that technical guidance. And now we're back to where we were before, of treating streams as a linear feature on the landscape. From a crediting standpoint, we still require, enforce design standards on a spatial basis. So even though we credit it in linear foot, this design process is still in place as far as the rigor and the science goes. It's unfortunate, the linear basis, because you could work in a tiny headwater stream. 100 feet of that is equivalent to 100 feet of a 30 square mile drainage. They are not equivalent resources. Our process addressed all of that and included in that technical guidance. It also included a process and a means for targeting and a rewarding targeting of resources and objective setting where we wanted them to go in the watershed as well. So, and that was supported by sound science. And again, it's unfortunate, but that's now been rescinded, and we're back to where we were which is basically no standards for impact identification or crediting, and it's just a linear foot basis. That's a whole week conversation if you want to have that. So I will give you, I like this slide because for a lot of people that aren't familiar with it, this has been a very difficult task for some people to grasp onto. We are in the process, or have been. It's been much more protracted, I think, than our program would like, or any of us would like. It's going on 2 decades now. 2/3 of my career has been spent dealing with this, and a lot of recalcitrance in understanding and moving to the trajectory or direction where we want people to move in terms of the science and the design approach. But we're shifting away from just evaluating the conditions on the ground as a basis for requiring or defending or demonstrating the need for work. What we want to do is develop comprehensive restoration projects that go through an evidence-based approach. And one of the key factors to this process is identifying historic alterations to the valley. And it's not just the stream channel. So it's all in many cases, stream channels aren't even in the location they're supposed to be in. They're on the margins of the valleys. They may even be outside of the original floodplain, and they may be perched up on the valley wall in many cases. So understanding that historic context, the alterations, this is really the basis for our process. And it's what we put bankers through. They've got to go and do good geotechnical work, investigative work, historical work, to understand what's happened to the stream and propose an approach that will address those degradation elements in order to meet the level of crediting to be awarded credits for restoration or rehabilitation. One of the principles of this is understanding historic or pre-alteration valley, that paleo condition. I'll talk a little bit about that later, and I'm sure Ward will too. That really is important to understanding how the resource has been altered and the underlying causes as well. But it is a critical element to addressing and developing a comprehensive restoration plan for sites. And again, as I mentioned, we hold banking industry to a very high standard, probably the highest standard in Pennsylvania in regards to restoration. And if they propose to address symptoms, DEP probably is not likely to approve their permit. If we do, it will be only a minor amount of credits that are awarded because they're not addressing the problems at the site. They're just addressing symptoms of much broader issues. And the longevity, therefore, is likely minimal. The projects won't last long either. The goal is here to restore things to self-sustaining ecosystem and fluvial system. So as Beth mentioned earlier in one of her introduction slides, terminology. This has been the bane of restoration. This is one of the things that causes more problems on a regional scale. This isn't just Pennsylvania. This is the entire mid-Atlantic, and I would imagine the entire country, actually, or actually the world, if you really get down to it. What is restoration? We use a very rigorous standard in the regulatory program for banking. These terms were developed out of the National Research Council's work in 1992, which is some seminal work that was done. For those of you who aren't familiar with the NRC report, I would suggest you go back and look at it because it's a really comprehensive look at aquatic impacts and restoration to wetlands and ecosystems. So we start out with that terminology right now, which these dovetail the federal definitions that are formed out of the 2008 mitigation rule, as well as these are part of the Federal Geographic Data Commission's standards, which are standards applied across federal agencies for consistency. We use, that's the guiding definition we use now is the mitigation rule, which is really born out of this 1992 report, and you can see that when you look at the definitions. But restoration's in 2 categories, and so when we do crediting, which category definition you fall in changes the amount of credit award you receive from a unit of area or a unit of measure. If it's streams, it's linear feet. If it's wetlands, it's acreage. So if you do reestablishment of a resource area, you get 1-to-1 credit. So for every 1 unit you restore, you get 1 credit awarded. If you do rehabilitation, it's now in a sub ratio of 1 to 1. So oftentimes it's 1.5 to 1. So 1.5 acres of work will get you 1 credit. Or it could be even up to 2, or the ratio isn't necessarily set in stone. It's also definable or a little bit malleable based upon the work you're doing and the level of work you're performing. And that's why the technical aspects and understanding some of the science is important, because that's what we're looking at to inform the decision making when it comes to crediting projects from a mitigation standpoint. And I'm not going to read these definitions to you, but these definitions are really important to consistently applying an evidence-based approach to evaluating projects, evaluating conditions in the landscape. This drives everything. I was just looking at a project proposal this morning for some funding stream. People were proposing projects. They said they were doing wetland restoration. They were planting trees and shrubs in an existing emergent wetland. That is not restoration. I don't care where you define it, how you define it. That is not restoration. That would be enhancement. So it's not, what is not restoration? Enhancement, establishment or creation of resources where they've never existed or did not previously exist. Those are not restoration activities, although these are often coined as restoration when people write their narratives and their grant applications and their permit applications. The terms are used very loosely and problematically. I would say in a lot of science that you read, a lot of literature that's published evaluating effectiveness of best management practices, evaluating the effectiveness of, in quote, air quotes, restoration. When you boil down and look at the really deep, if you get able to get down into that project and that research, what you're looking at is probably not actually restoration. At best, it might be rehabilitation. More than likely, it's enhancement. And that's one of the problems with relying upon some of the literature and the science is the science isn't, these researchers are not always, but in some cases, are cherry picking their terminology and projects, and then they're not matching each other. In some cases, it's just the use of the term has become so ubiquitous that people aren't actually paying attention to it anymore. And that's a real problem because it gives the underlying science, it gives these larger projects and these more comprehensive efforts, it gives it a bad name because these are expensive, these are time consuming, these are difficult to do. But when you're calling something as simple as plantings restoration, you're doing the more comprehensive work a disservice by doing that. One of the last things, and Beth kind of touched on this, is stabilization. This is, if you're putting materials to prevent erosion, to resist erosion or sliding or movement of soil, that's stabilization. That is not restoration. I think one of the things that people conflate or confuse is their programmatic goals are to restore or improve water quality. And they're implementing that through best management practices. But the goal is to restore or improve water quality, but the practice itself is not a restoration practice. That's the goal of the practice, to restore or improve water quality. But actually, many of these practices are not restoration in and of themselves. They're treating or addressing a specific item or issue related to the resource condition or degradation. And I'll talk a little bit more about that later. I'm going to breeze through these because I know we have limited time, and this really wasn't the gist of what you wanted to hear. So, but I think one of the things that I think is a good place for people to start looking at and understanding stream systems, fluvial systems, is stream evolution triangle. I like this. It's more, I use the term, it's like a theoretical construct. It's a framework to put your experiences and science together in to operate. But I think what's important here, and the change that this approach makes, is it brings biology into the evolution triangle, where in the past it's always been about hydrology and geology. In other words, water and sediment. Biology was just ignored because the people who did that work had no background in biology. And the fact is, when you look at the most stable systems, the most dynamic systems we have in relatively intact state, biology, the plant community, the vegetation is often dictating stream form, pattern and form, or your, it's influencing the other fundamental processes of water movement and stream and transport. But it can only do that under a certain domain, under certain conditions. Once you exceed those thresholds and start making changes on maybe a hydrology or geology domain, you start losing that ability of biology to dominate. And it's not just plants, it's also macroinvertebrates. It can also be other in-stream biota that can actually influence stream condition. There's some research that I've been following out in Montana that's looking at from National Science Foundation through, I think it's Montana University, that's looking at the effect that net spinner caddisflies have on stream transport and and stream bed stability. They've shown that that biota can effectively increase the stream bed's ability to resist shear stress by 30%. That's huge. You're increasing by a third the ability of that stream bed to resist transportation, shear stress conditions that would normally cause transport of materials downstream. So they're stabilizing habitats, gravels, and smaller particles. That's a big deal when you start looking at habitat and functions. So we really look at, when we evaluate these projects, banking is comprehensive. The goal is to develop comprehensive projects that address watershed and the underlying problems within a watershed. So we're looking at systems. We're looking at developing resiliency, and how you develop resiliency is through redundant pathways. Obviously, diversity and conditions, that can be a wide range of things. We're looking for diversity and ecosystem stability. And all of these things are reflected in the paleo environment and the historic conditions. If you do the geotechnical work and the past work to look at what that system looked like before it was altered, can be really informative. We're looking at retentive systems. These things retain carbon, nutrient retention, processing, transforming nutrients. So the nitrogen might come in organic, it leaves in a biological form, which is a completely different animal when it comes to aquatic resources. Fine-grained sediments are retained, smaller variety, more heterogeneity of sediments. So you have more diverse habitats, more diverse conditions that a much wider range of biological communities can survive and thrive in. Big issue is retaining groundwater and basal flows. Reestablishing the hydrodynamics connectivity is paramount. That's where it all starts from. So we're looking at groundwater, whether it's hill slope, whether it's vertical, channel flow, flood flow. All of those things are a factor into evaluating design, evaluating alteration, evaluating design appropriateness. Is it going to be successful or not? All of this stuff has been building on comprehensive work done by research across the world. U.S. Army Corps of Engineers Research and Development Center, or ERDIC, has identified over 60 functions associated with fluvial and stream systems. So there is a plethora of things related to fluvial systems, and most of those functions are outside of the stream channel. I hate to tell people that love stream channels, but it's about the broader fluvial system. It's not just about that in-stream, picturesque thing that everybody likes to do and drop their fishing line in. But we're also looking at long-term channel and floodplain dynamics. As I mentioned, diversity and evolution of habitat is really important. Hydrodynamics, this is where it's at. When I evaluate a project from a banking proposal, these are the things that I really focus on in understanding how have the hydrodynamics been altered? How does the proposal address those alterations? And is it going to reestablish these? I say they're on 3, it's actually 4 axes. There's longitudinal, horizontal, and vertical. There's also hill slope is kind of an independent process in smaller headwater streams. I don't have listed on here. I think I included in the horizontal or vertical. I can't remember which in the presentation. So these are the underpinnings of evaluating degradation, alteration, and a design proposal. This forms and significantly influences almost all of the major processes associated with a fluvial system. And if you're not undoing the damage or the alterations done to these aspects of it, then your project is not likely to have the outcomes that you're expecting, which is full restoration. I developed this to try to show you the complexity of hyphoric flow. You know, people often think of hyphoric flow as just a vertical movement of water, but it's not. There's a huge, horizontal and longitudinal spatial complexity to this. And this graph represents those different, upwelling and downwelling points along and across a valley. So you can think of these arrows in a two-dimensional space of along a valley and across a valley. You get a lot of different combinations of downwelling of water and upwelling of water. These are the biogeochemical hotspots that really transform nitrogen. And without this kind of complexity, you have a much reduced capacity to remove nitrogen from the system. I remember most of the nitrogen, I know the models all use edge of field, edge of stream. In my experience and based on the science I read, this is all coming from the groundwater. The nitrogen sources are in the upwelling of the groundwater from the sides of the hill slopes or the broader valley water. So if you don't have these complex processes restored and in place, you're going to have a much reduced capacity to deal with nitrogen altogether. It's pretty much just going to keep passing down valley flow in the stratigraphy or in the groundwater that's not being treated. It'll just keep moving to the next larger system. So the other thing you notice, there's a lot of redundancy here, and that's a big factor in having healthy communities, healthy ecological processes, is redundancy. They can withstand a lot more perturbation if they have redundant pathways. You still get, even if something happens to one pathway, you'll still have 3 or 4 different pathways that can take up the slack of that lost pathway. But at some point you oversimplify the system and you lose that redundancy, and then it becomes more of a linear process, similar to a structural BMP, more or less, which is very linear and very, has no redundancy to affect processed nutrients. So as I mentioned, summaries, hydrodynamics, that's where the action's at when we look at things. But how do you look at those? You need to deal with geomorphology. Geomorphology is kind of that bridge between the physical and the biological world. That's where things happen. That's where you build these redundant systems, restore them, and understand the potential of a natural unaltered valley. And the biogeochemistry is a combination of everything together: biology, geomorphology, and water. Without all of those things acting together, you have much simplified biogeochemistry. And there's a lot of good research coming out on especially how headwater and midwater sheds are the progenitors or the generators of biogeochemistry that really influence downstream water quality conditions. Without looking at the headwater and midwater systems, your downstream waters will not likely ever recover chemically or water quality wise. So watershed alteration. So this is what we drive these companies to, looking for characteristics that are divergent from historical stable systems. In this instance, you can see on the right, that's a typical legacy sediment. The legacy sediment is a light brown to tan material. As you move down, you see the black layer. That's the organic horizon, and the original hydric soil, and then the original gravels that are not supposed to be transported to a great extent are underneath that material. But we look at breached dams. If you see here on this magenta line here, that's actually a historic dam that was breached. This is a tiny little headwater stream. And you can kind of see in the LiDAR form that it looks like a lake. And sure enough, that's what it used to be. It's a big, flat, broad field now. You can see the light blue line is where the stream was relocated to the margin, maximizing agricultural use of that after dam breach. And then the tributaries that come in are head cut and ditched to effectively help drain the what sediment is there. Now these sediments are only 2 or 3 feet thick, but they still do the same thing as if they're 10 feet. They're burying the original wetlands in that valley. In some cases, there's now houses on these, which is kind of scary to live there. But you know, this is what we look for, these kinds of systems in small mid headwater streams. Obviously, you're familiar in Lancaster County with legacy sediment. You know, we instruct bankers. A lot of bankers aren't from Pennsylvania. They come up here. So, you know, the ones that are, it's a little bit easier, but those are out of state. We really take time to educate them on looking for indicators. You know, like the top imagery, these draped tree roots. You know, everybody talks about trees and vegetation stabilizing banks. You know, that bank eroded back 10 feet. And I can tell you that whole floodplain is forested with 60-year-old trees. And those trees are not going to stop that bank erosion. This is what happens. It just keeps undermining, the processes keep working regardless of vegetation, because the banks are not natural. These are legacy sediments. That's a 4 foot high, 5 foot high legacy sediment bank up in Perry County in the Ridge and Valley, for example. Same with buried stumps. If you see fragipans or ledges, clay ledges down where the stream channel is, or under the water surface elevation, that's probably the stream cutting back down to its original base level. And what's really important to understand with these restoration projects is that base level controls are what drive, or the loss of them are going to drive everything. And I think Ward will talk a little bit more about that. But that's where it's important to get back to, you know, how did this system lose its base level control, and how can we reestablish that control to reestablish the broader floodplain and systems that need to be there. Oftentimes, because they're cutting below base level control, they're now accessing bed load that was, you know, predated. I apologize, I just lost my you know, they go back beyond the previous ice age. They're activating bed load in parts of the state that were buried long ago and aren't supposed to be active anymore. But because we lost base level control, they're now cutting back down through those materials and activating them when they shouldn't be. The northern tier is a big area where this is happening, where Pleistocene gravel deposits in alluvial fans are being activated, and you know it's possible that once you get past certain points that you may never be able to stop these unravelings. And you can see this up in the northern tier in some extent on some of the bigger creeks. There's some good studies that are showing that happening. As I mentioned, alluvial fans, these are something people don't recognize often. A little more difficult to recognize in the Piedmont. They're much more subtle. In the Ridge and Valley and the Plateau region, they are much more predominant or easily observable. But you know, the ditching of streams and incising of streams down through alluvial fans. Alluvial fans are extreme hotspots for biogeochemical processing and generating of iron and manganese that's important and critical to nitrogen removal in systems. Not to mention they provide great thermal regulation of downstream waters. You know, this is a big chiller. Basically, it's a geothermal chiller. And so as water passes through that fan and ultimately, you know, comes out into the larger main stem stream, it's going to be at ground temperature, 46, 52 degrees. You know, it might vary a little bit seasonally depending on how deep the fan is, but you know, that's where your thermal regulation is, more so than through shading. One other thing that often is missed is head cuts. Again, this is loss of base level control. This is an active head cut that's moving up through, in this case, colluvium. So this is an extreme headwater channel that barely had a channel in it, barely flows. You can see it in the back image. It's only a couple inches deep, and there's, you know, maybe an inch to 2 inch, 3 inch banks on the actual form. The vegetation root mat is thicker than the stream banks up top in reality. This head cut generated and start generating as a result of a culvert replacement. They over excavated, didn't ensure base level control coming into the culvert was maintained. And so this head cut started propagating through this gentleman's property, and eventually it's going all the way up to the tree line up top. And I don't know, maybe it'll go further than that. I don't know how far the stream goes, but this generates a ton of gravel and material downstream that fills the channel, in which now the township is excavating on a routine basis, because all that gravel and silt that's coming out of there is going down there and depositing, because it was wider, an excavated channel. Now it's an ongoing maintenance issue. But vegetation alone is not going to stop these head cuts. Eventually, this head cut will undermine those two trees on the right, and they will fall hopefully to the left and not to the right, because the guy's house is to the right. I think I'm going to skip through effects of degradation. I think we've kind of talked about this a little bit already. Like I said, we are looking at understanding the hydrodynamics and how they differ between an altered and natural system. So we're looking at vertical, horizontal, longitudinal, but also in a lot of smaller systems, we're looking at hill slope systems, which when these legacy sediments are in smaller streams, oftentimes, as you see on the left, the hill slope arrows that come down, that water comes down and interacts with the valley groundwater. If it's there, if it's present. If it's not, then it dominates the fluvial system. If it's present when you have legacy sediments like on the right, what often happens is that legacy sediment presence caps those ability of that hill slope water to actually go and join the broader valley groundwater. And what happens is they express themselves on the back edge of the valley, right at the hill slope margin, and you'll get these little depression wetlands and wet seeps in areas in those areas. Those are actually an indicator of legacy sediment presence. And when we look and evaluate impacts, that's an altered condition still, even though those wetlands are present. What we might do is change the restoration category crediting to rehabilitation as a result of removing the legacy sediments, because those wetlands acres would still be present regardless of the sediments. So we changed the rehabilitation or restoration reestablishment down to rehabilitation, because they're wetlands, but they're also highly altered because of the sediment presence. And by restoring the hydrodynamics, they're rehabilitating those wetlands back to their former functioning, which is an important thing. So that's how we can do these projects and look at them. Even though there's wetlands on these projects areas, they're often highly altered and in response to the presence of the sediments. And when you remove the sediments, you end up creating, reestablishing more acres of wetlands, as well as rehabilitating those minimal acres on the back areas. And I see those in forested. It doesn't matter if it's shrub or forested areas, those wetlands are present just about everywhere. One of the biggest things that we're learning from our work in Robinson Fork, which is a 500-acre mitigation bank, we're researching and doing a lot of work. These restoration projects, which was demonstrated at Big Spring Run, have a significant effect on flood attenuation and the hydrograph. They really can change to a significant extent how the hydrodynamics work with flood pulses with storm events, which also influences nutrient transformation as well. As I mentioned earlier, we're looking at exporting systems under altered condition, and we're looking to restore these retained systems. I like this slide because it gets the point across. The problem has to be clearly seen. A banking must demonstrate that the resources are degraded. They have to identify the cause of that degradation, and then they have to propose, understand the potential of the watershed through understanding a paleo environment, and then propose a restoration plan that will address all of those things. If they don't, or there's constraints in the watershed that prevent that, it's not that the project can't be done. It can still be done. It may just shift how the crediting works. We may move from a restoration into or reestablishment into rehabilitation, or from rehab into enhancement as a result of constraining conditions. The one thing I do want to touch on before I kind of end is understanding paleo evidence and historic condition, it's not synonymous with trying to restore historic ecosystems. That's a misnomer that's been propagated over and over again. What it does is it provides evidence of the ecological potential of the site. And that's what you use to inform your target conditions and your target and your design perspective. It tells you what's potentially possible at that site physically. The biological aspects, ecological is a separate consideration, and we are developing and have developed tools to assist in community restoration, community development, and targeting planting and ski. And we'll be providing training later this year on that. So, last thing I'll settle on. This is I've been waiting to use these little kitty cats for a long time. My kids make fun of me because I collect weird pictures here and there. This isn't an us versus them process. I think if all of the stakeholders and project proponents can come together and utilize terminology consistently in a standard evidence-based approach, we have a better understanding of well, using an evidence-based approach and standardized terminology will reduce conflicts among project proponents. But what the other thing it will help do is improve the understanding of expected outcomes. People are expecting restoration of resources using certain BMPs because of the terminology it's used. The public doesn't understand the distinction. But the reality is you're not going to get restoration. You might get some improvements or reduce pollutant constituents from entering a system, but you're not going to get restoration. And I think this has been a pervasive problem for many years, and obviously it's something that's not going to go away overnight either. That's it.
Thanks so much, Dave. I think we're going to continue to hold questions to the end, if that's okay with everyone. I will turn it over to Ward Overholtzer from Land Studies and Century. If you could, Ward, are you still there?
Yep, I'm here.
Okay, all right, awesome. Are you good to share your screen? Or would you like me to bring your presentation up for you?
See if that works.
Okay.
Did that
You're
work?
good. Yep.
Okay.
All
All
set.
right.
Thanks so much.
Sure. So I'm going to discuss about restoring the hydrologic functions on a watershed scale, and typically it's done through mitigation banks as opposed to project by project. As Dave alluded, the reestablishment is focused on returning natural functions to the site or the watershed. That may very well include larger waters leading all the way down to finger streams or zero order streams to the hill slopes. We're looking at everything from base flows to flood events to try to get those hydrologic functions reestablished. I'm not getting, why am I not being able to?
If you click on your screen and then maybe hit the right arrow, that might.
There we go. Okay.
Okay.
As Dave alluded, pretty much all of the valleys and hill slopes and everything have been altered historically, from the logging, railroads, agriculture, you name it. As you can see in here, part of the logging systems occupied pretty much the valley bottoms. They were flat, they were available to use. They manipulated everything again from the head slope, the hill slopes to the headwaters to the larger river valleys. Agricultural practices were ubiquitous. So was ditching, straightening of the channels, relocating of the channels for agriculture. You had maybe mining for subsidence, and then you also had dams that would actually raise the valleys. And that kind of comes in play when you're deciding, where your base controls are. Has your valley been raised? Has it been ditched? Is it draining the floodplain? Is it forming gullies? Where did your head cuts originate from? You had major increases in soil from logging to mining to agriculture. Same thing, pollutant and sediment inputs. Strip mining areas, streams start to migrate into some of the comb piles or the waste piles. You end up with a ton of sediment working its way down into towns and filling the bridges and the channels. Here's a comb pile that was over 1,000 feet long, 50 to 80 feet high. The stream was flowing into it. The town, Donaldson and Tremont downstream, start to feel the effects of increased flooding due to all the deposition coming within that town. As Dave alluded before, we have to understand the pre-alteration of the valley in order to really provide a comprehensive restoration. That this could involve agriculture, it could involve mining, subsidence, dams, etc. What we realized then is we've got to do our work, our homework, figure out what's going on with the subsurface, what's going on with the surface, and having a good idea on the watershed. On Big Spring Run, which is kind of used as an example in many locations, you can see where we had the post-settlement alluvium. And as Dave indicated before, we have the pre-settlement floodplain and the gravels. They do pollen tests, magnetic susceptibility, carbon testing, et cetera, to get an idea of the age of the soils. And this had occurred probably a decade to 2 decades ago. Not that we still don't do a lot of this, but there's a better understanding now than previously. Things you see in the field give you an idea too that something's not right when you have buried stumps that are 10 feet below the top of a bank. This is Little Gunpowder River, very close to this is actually tidally influenced. Imagine how much sediment is making its way to the bay in that short distance. Same photo that Dave had, you can see the buried stump. This is out at Ryerson in Western PA. So in essence, what we ended up with impacts from the European settlement. We've got major soil loss from the uplands, changed drainage patterns, increased transport of soil and nutrients. We've gully formation in the smaller streams, hill slope failure itself. Hill slope failures and slides are the results of that. You really don't have an idea of base level controls until you start doing your homework. You've got then your floodplain encroachments and your channel straightening and stream relocation, et cetera. So it takes an awful lot of information up front before you can go into determining a design for restoration of the values. Again, the top shows kind of the legacy sediment feature. Primarily, a lot of this was done with some type of floodplain encroachment with a dam or a roadway and a small culvert or railroad, which significantly increased the base level control for the valley, raised the valley. Then you get incision, and the channels actually incise much deeper into the bedrock area than they were previously due to high stress and high velocities. Well, now we got to figure out how to restore those functions, get it base level controls back, get the interaction, the hydrodynamics, the connectivity, et cetera. A lot of people think that it's just imperviousness that causes stream degradation. This is out in Frederick County. We had major long-term bed degradation through this county. The chart right here indicates the long-term bed. To the left is feet, is we measured how much long-term bed degradation had occurred as a research project for Maryland State Highway for their bridges and culverts and fish passage. And then to the bottom, you have the impervious area. Well, you'll see that major degradation occurs where the percent of impervious area is least. A lot of people don't understand why. What happens is, as the impervious area increases, you end up with more roads, more culverts, more utility crossings, more impacts across the channel that actually stop the long-term bed degradation from getting deeper and deeper because you have nick points. You drop a culvert, then you end up with that head cut continuing to migrate upstream. This is stream evolution. once you start getting bed degradation and incision, your higher velocities, your higher boundary stresses, then are transport and eroding. You get lateral migration. You get an evacuation of the soils and the nutrients. You get a constant, I'm going to say, disturbance of your epiphytal substrate. And by the time you get finished, you end up having the stream migrating, removing the majority of the sediments and going back to a zero order system. All right, so watershed scale restoration may very well require a wide variety of drainage areas and streams within it, including the uplands and the hill slopes. As you can see, what we're looking at for restoring those functions on a watershed scale, we want to understand what's happening with the uplands, what's happening with the hillside seeps and the zero orders, the narrow and wider valley systems, and the larger drainage areas. Included in that are transition zones too, like alluvial fans, or we've got to worry about how we're transitioning upstream and downstream of the properties and whether we have a high bed load system coming in or not. What we're typically trying to do in most cases is provide low stress design techniques to create a retentive system like David talked about, where we're retaining the carbon, the biology, the sediment, you name it. We want to hold everything in place. And then the other features that we're trying to improve or try to restore, a longer duration of base flow, higher base flows, a more consistent temperature, whether it's cooler in the summer or warmer in the winter, a stable substrate for spawning, etc. And then obviously greater vegetative diversity is featured. So the uplands and the hill slopes, we're trying to possibly reduce or replace lost soils and nutrients. Sometimes when we take the legacy sediment that's formed in the valley, we can reapply them to the hill slopes and the watershed for agriculture. Habitat will restore meadows, especially in locations where bedrock is shallow, buffers, use it for contaminated lands, etc. The hillside seeps in the zero order streams. These waters typically are found in silton soils. They're not usually what you would call substrate or conditions where you will have a single order stream. Many times there should actually be just a wetland or a marsh, not necessarily even having any type of channel within these systems. They provide vertical control. They provide retention for carbon, for water, which is important to the base flow, sediment, etc. They process a lot of nutrients, and then they provide a lot of groundwater storage for a longer duration base flow to the larger waters. On the left, you'll see a gully that's forming within a zero order system. And to the right, we actually raised that gully about 8 feet through this tributary. There is a channel going through there. Preferably, there shouldn't have been a channel. We would have rather loaded it up with woody material, but because it was a mitigation site and channel length was required, we ended up putting a small channel within that system. The steeper systems that have narrow valleys, maybe it might be half a square mile to 3/4 square mile, 1 square mile, somewhere in that area, with subsidence occurring, where you might end up with parts of the valley dropping 4 or 5 feet. You end up with a much steeper, narrower valley than what you may have had naturally. Now we've got to worry about how we're keeping the groundwater up on the surface, our base level controls, our vertical controls. Are we using colluvial material, bed material, logs, etc.? We prefer to try to use base off of bedrock that's what the groundwater, the aquitard is, try to get a substrate in there to provide for the substrate, it's epiphytal substrate, etc. Again, you've got the retention issues. We're trying to retain everything from the sediment, groundwater, carbon, etc. Slower we release it, the more biology we get, the easier it is to keep the invasive vegetation out as long as it's wet and saturated. This was to the left, Holly Hollow. This system actually did go through some subsidence. You can kind of, there's hill slope failures going on through here. To the right is how we would typically restore one of those steeper, narrower valleys. You can see a lot of the cobble, the bedrock associated with it. We put log controls in, etc. Streams with wider valleys, little more easier to deal with. Vertical controls may also have included beaver. The habitat diversity, you've got an awful lot more water. You have a lot more area to really take advantage of the salamanders, the substrate, the spawning, etc. There's also a lot more nutrients being processed in those wider valleys. Because they're nowhere near as steep, you get an awful lot more retention and processing. And then you typically end up with an awful lot more of a diversity within those areas. This Ryerson Station, this Kent Run, this is about a 3 square mile watershed, and Beeham is very similar. To the right, that was part of that mitigation bank, that RES Robinson Fork mitigation bank. The larger drainage areas I'm going to say are typically somewhere above 5 to 7 square miles. Again, the vertical controls, that's what we're looking at. The retention, the diversity can be excellent through those areas. But then we also now are trying to provide a recreation. May not necessarily have been part of the reestablishment, but where we are today, we're trying to include fishing, kayaking, etc. Ryerson Station to the left is where we had, they had to breach a dam. It's 33 square miles. We're in the process of putting a design restoration package together for permitting. Robinson Fork in this location is about 13 square miles. Then we end up with alluvial fans, which, as Dave indicated, are very critical for the groundwater and the processing. But they're also extremely critical to maintaining base controls for the steeper slopes and the hill slopes. If they start to get ditched or incised, then you end up with an awful lot of sediment supply and possibly nutrients entering the system from the hill slopes and the gullies. These alluvial fans are typically steeper than the headwater streams and obviously much steeper than the valley that they're tying into. And they can be, I'm going to say, a challenge trying to put together. This is an alluvial fan. On the left, you can kind of see the head cut and the gully just forming. You can upstream of it. It's not quite as incised, but that head cut will go quickly because they're also typically pretty steep. On the left, you can see how we designed a trib leading into an alluvial fan at the bottom within the Robinson Fork. Typically, they need to be relatively wide or controlled with a large type of material. The area to the left, once the alluvial fan got into the valley of the larger Robinson Fork, you end up with an awful lot of, I'm going to say, habitat for fry of the year and fingerlings, etc., through that thick vegetation cover. And a lot of it might have to do with the cold water coming out of that fan down into the larger valley. The transition is one of the last things that we need to actually try to look at. We've got to try to make sure that upstream of our project site, there's not significant change in stress. On the downstream side, it's usually easier. It creates kind of a backwater condition. We may be able to do different things. The restoration site as a whole is pretty much improving the downstream waters because we're actually containing, we're retaining a lot of the bed load, a lot of the silt, and a lot of the nutrients are being processed within our site. So primarily, I would say the upstream transition zone and what the objectives would be are more important. What in these transition zones at the upstream end, we typically may have to put in what we would call a sediment management zone or a sediment management area. At some point, more than likely, your restoration is going to end and tie into a very unstable system. On the left, you'll see Maryland 25 at Georgia's Run. Prior to a very short, I'm going to say, stabilization project, the large bar was forming at the bridge structure and the stream was eroding into the roadway embankment. What we did was go up far enough to develop a sediment storage zone. And this bed load was not actually coming from the main stem, but it was coming from a tributary that had been relocated and incised on a hill slope. So now we have that depositional zone away from the infrastructure. And now there's no need for constant repair work of the crossing. On the right slide, that is an area coming out of an area that experienced subsidence and mining. We had put in a large pool so it would not affect the restoration downstream. That area then became underwater as the beaver moved in. And I'm finished, Beth.
Thank you very much, Ward. And so I think right now, if anybody has any questions, this would be a good time to ask. Now we have no questions so far in the chat box, as far as I saw, other than whether the slides would be shared. So if anybody has any questions, feel free to unmute and just join the conversation at this point, since the presentation portion is over. So we can go ahead and do that. Anybody?
Beth, it looks like we have one in the chat.
Oh, awesome. Want to go ahead and share?
Rebecca is asking, how do you factor in regional differences in geology and vegetation with the reliance of research from the Midwest and potential differences in geology and vegetation? There are, I'll let you answer that one first. Or could you point to studies that are specific to the region?
I think that would be a good question for Ward. Did you get that one, Ward?
No, I was actually looking at the screen. What was the question?
It's how do you factor in regional differences in geology and vegetation with the reliance of research from the Midwest and the potential differences in geology, vegetation, et cetera, from the Eastern US? Or could you point to studies that are specific to this region that you use? If not, is that a gap that needs to be addressed?
I would say I've done work in Western Maryland, Midwest, and the East, and there are definitely significant differences within the geology. It does pay, I would say, to actually have somebody with you that is familiar with those regions. What we find though is the processes and the design techniques typically hold throughout the different regions. The controls would be significantly different. If you're interested in groundwater control or base level control in a coastal plain, it's going to be different than in the Piedmont, or different than the Plateau, or different in the Midwest or Western. But primarily the process is the same no matter where you are geologically. Same thing with the regions. Some regions are flat. You can do an awful lot of different things and you get stability. Other regions that are extremely steep, then you really pretty much have to rely on certain items, whether it's rock or wide valley or different things to create sustainability in the steeper areas.
So basically it translates for the most part across different geologies and different regions and that type of thing. But it's always good to consult local expertise, it sounds like too.
Yeah, I would echo Ward's experience. This is Dave. I've reviewed I don't know how many projects now with banking, and they've gone all the way from northeast down to southwest, down to the coast, or out into Philadelphia, and the fundamental processes are still the same. Your materials shift and change, and what you might use to control base level, as Ward indicated, might shift. You might want to focus on different materials based on the geology, because you might not have, like out in the Southwest Plateau where it's degradable shales, you might focus on using more large woody debris and vegetation to maintain base levels, where in a area where you have a lot of rock, you would focus on using the rock, the natural materials that are present. And that's what we recommend the banking companies look at in their designs, is what's natural to that area should inform your decision making in your design. It's pretty simple.
Okay. Anyone have any other questions, either in the chat? Oh, Scott, go ahead. I see your hand up.
Thanks, Beth.
Mhm.
Question for Dave. Dave, could you talk about how credits rely on, or how you map a credit that's generated from a project to a certain biological outcome, whether that's like paraphyton diversity, diatom diversity, or a fish or a macroinvertebrate like IBI score, and how you would set that score, that threshold that you have to achieve to generate a credit?
Sure. Well, one of the things I can say is I have early on adopted an approach of not using biological metrics, such as macroinvertebrates, fish, or paraphyton, because there are too many variables outside of the project's control that might influence response. And here's the big and, most of the IBIs that have been developed over the decades, and I don't care where you are, this probably applies, is they were all developed for certain specific reasons under certain specific conditions. And most of those conditions, in other words, their reference domain, were altered systems. So we coordinated with, for example, Robinson Fork Mitigation Bank out in Southwest PA that I spoke of, and Ward talked about in his presentation. When that project came up, that was, it's probably the largest bank, most comprehensive bank project east of the Mississippi that I'm aware of. And it involves such a range of conditions and resources that I don't think that in alone is probably unique in the country. And so one of the first things we did was put together a multidisciplinary team in DEP's perspective. So I pulled experts from a variety of DEP programs for pulling their expertise in from that program perspective. And one of those was water quality. And the first thing that came out of water quality pretty quickly was our IBI won't work here. It wasn't developed with these systems in mind at all, or there was actually zero data from these kinds of systems used. So there's a problem with most of the biological monitoring metrics that exist today, and it's a significant problem, not just in PA, it's nationwide, worldwide, and there's a lot of work ongoing to try to resolve that issue. And there's a bunch of papers that have been published over the last 5 to 7 years on this issue, and DEP has been funding research out at Robinson Fork for long-term monitoring to improve the approaches, or to develop ancillary monitoring techniques that, since we can demonstrate the biology responds or the processes change, you don't need to measure those changes. You need to measure this physical alteration or this observable condition. And we've seen that so far, and we're just hoping the publications will come out in another year or so. So what we tend to focus on are physical processes that you can observe. Flood flow access to the floodplain, As I mentioned earlier about net spinner caddisflies, I'm trying to wait patiently. COVID has kind of screwed things up for a while with research for everybody. But there's the studies on the net spinner caddisflies. You know, we see them, we see their diversity, their densities change radically. I mean, unbelievable. I've never seen such high densities in stream beds before after these projects. And so that's an indicator that shear stress conditions are dropped, as well as floodplain access and the modeling, you know, verifying modeling through observation. So we're focusing on those physical, tangible, measurable conditions. Vegetation's kind of a tough one because you're planting everything. So what's your target? At this point in time, for most projects, we require is what we call a comprehensive overplanting. So we plant all three vegetative structure classes. Herbaceous, shrub, and trees are planted over the entire bank site. Now, mind you, these projects on average are 2 to 3 miles in size. So these aren't little projects. These aren't 500 feet. You know, you're talking about 15,000, 20,000 feet of stream and valley, or valley, not really stream. And what we do is we as long as vegetation's healthy, vigorous, I don't care what survives, where it survives, is the approach that I've been taking. I've been having problems with other agencies that don't quite understand the adaptive management approach to monitoring like this, because it doesn't fit the historic norm of, well, you said this is going to be forested, therefore a tree has to grow here. If you can predict the hydrodynamics on these systems, you deserve a PhD. I don't know how anybody can do that, yet people expect them to do that when they do develop monitoring plans and performance standards. It's ridiculous. You have to be, unfortunately, people aren't adaptive and responsive to the projects, and, you know, get boots out on the ground and look at it. Is it healthy? Is it, you're going to have, trees won't survive where there's too much water. You know, herbaceous material will flourish, and shrubs will be somewhere in between. It depends on valley confinement, the, you know, hydrodynamics, the water power, the shear stress, you know, material, the material that's there, the geochemistry is going to drive what thrives where it thrives, and it's unpredictable. It's not, you can't predict the locations necessarily for planting. We are moving towards a community-based planting approach, a community targeting approach. I kind of mentioned it really quickly, is we did spend a lot of money in working with DCNR and Western Pennsylvania Conservancy to develop a restoration community predictor tool, the RCPT, which is on the Natural Heritage website. It's available now. There are some guidelines on there how to interpret it, but you really need a botanist to kind of tease it, because it gets you to a region, and then it gives you 40 different wetland community types or floodplain community types. So you really have to, you know, it gets you down to a narrow region, at least physiographic province. And then you have to start looking at how do you adapt that community predictor to the sites themselves. And that's kind of where, unfortunately, lack of staff and time, we are working on other tools to help do that. Mapping tools for valleys that rate valleys and conditions that will hopefully help do that in time. But there's only one of me and 40 people's worth of work to do every year. So
Thanks, Dave.
Beth, we have a hand up from Joe Sweeney.
Go ahead, Joe.
Thanks, folks. Great presentation, Dave and Ward, as usual. Great summation. My question is, Dave, I want to go back to an earlier remark you made early in the presentation about the rescission of the technical guidance. And I was wondering how that impacts the proposed in lieu fee that would obviously fund a lot of conservation projects in the Commonwealth.
well, it's definitely a problem. The in lieu fee still doesn't have federal approval. In fact, we haven't submitted it for review at this point because of that occurrence. The in lieu fee structure, and a lot of it was based on doing function-based crediting. And we're still not, like they did establish a small work group to evaluate the effectiveness of the technical guidance that was effectively not implemented. So you figured those words out. So right now it's kind of like in hiatus. It still exists. We are still collecting money primarily for wetland impacts, because people have an opportunity to still use it for streams, but nobody wants to step over that threshold and set the precedent. And it's kind of interesting because I know the numbers behind the scenes, and I can tell you, people are losing money, but that's their option. So hopefully that work group, I don't know when they'll finish their work, we'll make recommendations, and we'll know how crediting is going to go in Pennsylvania. And honestly, until that's done and dealt with, it's hard to finalize the in-lieu fee program. Again, I'm the primary person working on that, and I don't have a good direction to go in, and all the financial analysis has to be redone. We have to do the credit demand analysis, has to be reworked. The financial credit fee structure has to be reworked based on the outcome of whatever the recommendations are. And so until that's done, we're just kind of like, okay, we're here, but can't get a federal approval. So if you have state impacts that don't require federal compensation, the in-lieu fee program is a potential option. However, we do enforce and still require the use of the technical rescinded guidance on a voluntary basis to use the ILF program. And people are choosing to do that because it's cost effective. They're saving money, and for wetlands at least, and they probably would if they did it for streams too. But it's a dynamic issue that won't resolve itself anytime soon because of the rescission of the guidance. Which I think was unfortunate. It wasn't given its due consideration, I believe, but I'm biased. I'm the author, so just throw that out there. I'm
Thanks.
biased.
We have one more. We have another question here in the chat, Dave. What is recommended to be done with highly impacted floodplains in the near term when most of them will not receive these approaches of comprehensive restoration, perhaps for many decades, if ever? Also, is DEP trying to guide mitigation projects away from relatively healthy forested streams to heavily impacted unforested streams / floodplains?
Well, I'll address the first question or the last question first. When we evaluate the condition of resources, vegetation is not really evaluated or considered at all. Because if there are underlying alterations that are driving that are driving the fundamental processes of the resource, that is what is driving conditions, not the vegetation on the land surface. I've seen, if you look from a Landsat an image photo, a watershed, it looks perfectly healthy from a vegetation standpoint. When you get on the ground and get underneath the trees, it's horrific. They're not stable. So using vegetation as a proxy for condition is not something we allow. We require on-site analysis of hydrodynamics, geomorphic base level control, looking at modeling shear stress conditions for existing condition is a driver of condition as well. The thing that you have to be careful with in some parts of the state where splash damming occurred, you have streams that, water quality wise, they're healthy. Hydrodynamically or geomorphically, they're unhealthy. They're out of sequence. They're out of whack. So, it depends on what your objective is. Our objective is much broader than probably any other DEP program there is relating to streams and floodplains. We look at the entire system and its components and whether they're healthy or not. And if they aren't, then that's the basis we use to evaluate the need for interaction or intervention. As far as the first question is, that's a good question, and we've been harping on that for a long time here. And why everybody is, very little money has ever been spent on objective setting and priority setting. Can you show me how many studies have been done in PA on that? Our technical guidance that was rescinded, and when I say that, it's not just from a land cover, land use basis. because in many cases, I've seen these projects you can do this work in urban and non-urban environments. It's those two things, the land use and surrounding land, a factor into the design and approach, but you can restore these systems in both environments. So the problems aren't necessarily associated with the modern land condition or modern land use conditions in the area. They're broader than that and are underlying. And those are what constrain recovery and resource recovery. So I lost where I was going with that. but basically, in a broader context, our technical guidance set priority and objective setting for restoration projects for banking that we found were based on sound science and based on hydrodynamics and geochemistry. And obviously we factor in restoration approach. So that was a big factor in how to do that. We focused on the headwater to midwater systems, and eventually you look at it, unconfined valleys at that conjunction point are really good spots to go because you can pretty much capture upstream, the degradation coming off from upstream, or improve those conditions in those mid watershed areas and unconfined valleys. But that's for our program. Other programs, haven't engaged in that activity or discussion.
All right, well, thank you very much, Dave and Ward, and of course, Allison and Lancaster Clean Water Partners for getting everybody together. If there are any follow-up questions, we will, I see there's one in the chat, we'll address them in an email. Also, all of our contact information is here on the screen, so feel free to reach out individually. Just to be respectful of everyone's time, I think we'll go ahead and end the meeting as is right now. But again, like to thank everyone for joining. And Allison, do you have anything else you'd like to add?
Thank you so much for our presenters today and for our participants and your questions. I know that there are going to be some follow-up pieces that we'll need more information about, or that we may be contacting both parties about about addressing each of those kinds of follow-up questions. So keep the questions coming in the chat if you want to, and we will get you more resources via email after this.
All right, thanks so much, everyone. Enjoy the rest of your day.
Take care.
Bye.
Thanks.